Okay, today we're talking about section 4.3, concavity, points of inflection, and the second derivative test. All right, so a graph is called concave up if the tangent lines lie below the graph and the slopes of the tangent lines are increasing, which means f double prime of x is greater than or equal to 0. And a graph is concave down if the tangent lines lie above the graph. That means the slope of the tangent lines are decreasing, which means f double prime of x is less than or equal to 0. In class, we're actually going to go over sketching the first derivative and the second derivative from the original function, which will kind of help you understand this a little bit better. But just kind of a rule to remember when you're looking to determine the concavity. Concavity has two C's in it, concave, so we think second derivative. Two C's, do the second derivative. If it's concave up, it's smiley. Positive people are happy and smiley. If it's concave down, those outputs are negative, and frowny people are kind of negative, grumpy people. A point of inflection, P.O.I, only occurs when the two conditions are met, that the graph has a tangent line at that point and the graph changes concavity at that point. So the big thing is that people forget to check if there's a change in concavity. We cannot have a point of inflection if we don't have a change in concavity. So the graph of x cubed has a point of inflection at 0, 0 because we change from concave down to concave up at that point. All right, so just looking at this first example, we're not really doing any calculus here. We are just analyzing what the graph looks like. So the first question is, on which intervals is the graph concave up? So for concave up, we're just looking basically where this graph could hold water, right? It's like an upside down or like a cup, okay? So that happens from -2 to -1. And it also is going to be considered concave up from 1 to 3. And then again from 4 to 5. All right, and then we are concave down from -1 to 1. And then again from 5 to 6. On which interval does the graph have no concavity? So with the no concavity, basically you just kind of ask yourself, can I, for concave up, can I hold water in this? And concave down looks kind of like a mountaintop. So from 3 to 4, we just kind of have a linear portion of that function. So there's no concavity from 3 to 4. And then again over here from 6 to 7. Okay. And then points of inflection. This is where we have a change in concavity and the graph has a tangent line. So we have a point of inflection. At -1, it has that quick change, so we wouldn't count that as a point of inflection, but we have kind of that gradual change from concave up to concave down at 1. And that's a point, so we need a y coordinate with that to correspond to that x, and we'll get that in just a second. And we also have a change in concavity, that gradual change happening at 5. So we have points of inflection at 1, x equals 1, and x equals 5. So when we're looking for the point of inflection, we're just looking at the original function and seeing its output. So at 1, my output is 1. And at 5, I also have an output of 1. So those are my points of inflection. So to analytically find where a function has concavity and points of inflection, we are going to use the second derivative. This is very similar to what we did with the first derivative to check for increasing, decreasing intervals and relative extrema, but we're applying that concept to the second derivative. So this first example where we're going to actually use the second derivative asks us to determine the points of inflection and discuss the concavity for the graph of f of x equals x to the fourth plus x cubed minus 3x squared plus 1. So we always want to start with the domain. So the domain for this function is all real numbers, so we don't get any excluded values. Our first derivative is 4x to the third plus 3x squared minus 6x plus 0. And our second derivative is 12x squared plus 6x minus 6. So we essentially want to get the critical values for the second derivative. So we want to see where it's undefined and also where it is equal to 0. So this is a polynomial function, so it is never undefined. So f double prime is never undefined. And then we want to see where it equals 0. So if you notice, we can factor a 6 out of this and get x squared plus, 2x squared plus x minus 1 and set that equal to 0. Just divide off the 6 and then we can factor the 2x squared plus x minus 1. That will factor into a 2x and x equals 0. That will be a plus 1 and a minus 1. Let's check that real quick. So 2x times x is 2x squared plus 2x minus 1x minus 1. Perfect. All right, so our critical numbers from the second derivative are x equals, didn't mean to change that. Our x equals 1/2 and negative 1. So these are the numbers where I'm going to put on the second derivative number line, and these are possible points of inflection. So possible points of inflection. So in order for them to actually be points of inflection, we need to have a change in concavity. So we're going to test these on a number line with the second derivative. So we're going to plot those on our number line, our possible points of inflection, and then plug a test value into that second derivative. So I'm going to be using this kind of more simplified form of my second derivative, a little bit easier to test signs in that factored form. So a number between negative infinity and negative 1 would be negative 2. And we're plugging that into our second derivative. So 2 times negative 2 is negative 4. Negative 4 minus 1 gives me negative 5. And negative 2 plus 1 is a negative 1. So we'll get positive outputs between negative infinity and negative 1. Okay, a test value between negative 1 and 1/2 is 0. And we'll plug that into our second derivative. 2 times 0 minus 1 is negative 1. 0 plus 1 is 1. Negative 1 times 1 is a negative output. And then an easy test value between 1/2 and infinity would be 1. So 2 times 1 is 2. 2 minus 1 is 1. and 1 plus 1 is 2, and that gives me a positive output. All right, so analyzing what this means. I'm just going to go ahead and erase this, give us some space. So if I have positive outputs for the second derivative, that means that this is concave up for these two intervals, and a negative output for the second derivative means we have concave down. So we are, let's go ahead and erase this. So to analyze the concavity, we would say we are concave up on the intervals from negative infinity to negative 1, and from 1/2 to infinity. We are concave down from negative 1 to 1/2, and then we have points of inflection at negative 1 and 1/2. The way that we know we have a point of inflection is we have a change in concavity. So we went from positive to negative, so that's concave up to concave down, and then from negative to positive, so concave down to concave up. So points of inflection at negative 1 something and 1/2 something. So to figure out what the actual point of inflection is, that is an output or a y value, and that goes with our original function. So our original function is f of x. No. Oh, sad panda. We can pick up where we left off. It's okay. All right, so we were finding our points of inflection. So that happens, we said, at negative 1 something and 1/2 something. Okay, so it's just really important to remember that when you're finding an actual point on the graph, that you plug your x value into the original function, which we have here. So f of negative 1 will give us an output of negative 2, and f of 1/2 will give us an output of 7/16. So we have a point of inflection at negative 1, negative 2, and 1/2 7/16. Okay. So with example 6, they are giving us the original function and have calculated the second derivative for us. And we are asked to list the intervals where the graph of f is concave up, concave down, and list the points of inflection. So with this, looking at our original function, the domain for the original function is going to exclude positive and negative 2, because that is what's going to make this denominator equal 0. That's where we have vertical asymptotes. And so that's where something could possibly be changing with the graph. And then we want to get our critical numbers from the second derivative. So our second derivative, if we tried to figure out where that equals 0, it would be setting the numerator equal to 0. And from solving this, we can see that we won't have any place where the second derivative equals 0. Divide by the 10, give us 3x squared, subtract the 4, and as you can see, we'll get imaginary solutions. So f double prime of x is never 0. F double prime of x is undefined at x equals plus or minus 2. Again, zeros of the denominator. So it's really important to note that where the second derivative is undefined will not give us a point of inflection. So that goes with like the definition of a point of inflection. The concavity has to change at that value, and it must be differentiable at that value. So these are vertical asymptotes, and we can't take the derivative on a vertical asymptote, so that we won't have any possible points of inflection. So these are not possible points of inflection. Okay, that's just where our second derivative and our original function is undefined. So really what's in question now is the concavity. So to analyze the concavity, we are going to do a number line sign analysis for F double prime using 2 and negative 2. All right, so we are just plugging a test value into our second derivative. So this is a second derivative analysis. So let's plug in, let's see, something between negative infinity and negative 2. Let's just do negative 3. So we're plugging that into, remember, our second derivative. So negative 3 into our second derivative will give me, let's actually erase all of this just to have some space for us to do those calculations. So we are plugging negative 3 into our second derivative. So F double prime of negative 3 will give me 10 times 3 times negative 3 squared will give me 27. 27 plus 4 is positive 31. And then in the denominator, we'll have negative 3 squared is 9. 9 minus 4 is 5 cubed. So this is going to result in a positive output. All right, next one, let's plug in a number between negative 2 and 2, so F double prime of 0. In the numerator, I'll get 10 times 4, so 40, over negative 4 cubed will give me a negative output, because negative 4 cubed has an odd amount of negatives, so this will be negative. And then finally, a test value between 2 and infinity. Let's do 3. So when we plug 3 in, we'll get a positive on top. And 3 squared is 9, minus 4 is 5 cubed is a positive. So we have positive. Again, just like we talked about with the first derivative test, we can't always assume that we're going to have a sign change. We need to check those every single time. So analyzing the concavity. This graph is concave up from negative infinity to negative 2 and 2 to infinity, concave down from negative 2 to 2, and no points of inflection. Okay, these values of negative 2 and 2, it might help if you put kind of like drew a vertical asymptote there to help you remember that these are not possible points of inflections. They are just where the graph is undefined. All right, so the second derivative test for relative extrema. We have the first derivative test that that tells us where the graph is increasing and decreasing, and therefore tells us where we have a relative max and min. The second derivative test for relative extrema is is kind of one that you only use if the directions tell you to do that or the information requires it if you don't have enough to get the first derivative. The first derivative test is better for determining increasing, decreasing, and relative max and min. But sometimes we have to use the second derivative test. Sometimes the second derivative test is inconclusive. If you ever get this, when you're if you ever get a result of f double prime of x equals 0 when you're testing the signs, then it's inconclusive and you have to refer back to the first derivative test anyway. The way that you do this is you're going to use f prime to find critical numbers, and you plug those critical numbers into the second derivative to analyze the concavity. And from that concavity, we can determine whether we have a relative max or a relative min. So if something is concave up, our outputs would be positive for the second derivative, and that would mean that we have a min. If it's concave down, it's frowny, which would mean that we have a relative max. Okay? So use the second derivative test to find the relative min and relative maximum points for the graph f of x equals negative 3x to the fourth plus 6x squared. So since they're specifically saying use the second derivative test, we will find our second derivative. So f prime of x is negative 12x cubed plus 12x. And our second derivative, and I left a space there because we need to find the critical numbers from the first derivative. Our second derivative will be negative 36x squared plus 12. So we still need to get our critical numbers from the first derivative. We can factor out a negative 12x, which will leave us with x minus 1 equals 0. So our critical numbers are x equals 0. Let's see, that's actually supposed to be a squared right there. So negative 12 equals 0, divide off the negative 12, we get x equals 0. Solving this piece, we get x squared equals positive 1, square root both sides, remember plus or minus, we get x equals plus or minus 1. So those are the critical numbers. So when you get the zeros or where the first derivative is undefined, those are critical numbers. When you get the zeros or where the second derivative is undefined, those are possible points of inflection. So with the second derivative test, instead of making a sign number line, we are actually plugging these critical numbers into the second derivative and seeing what type of output we get. So f double prime of 0 is going to be 12, which is a positive output, so we're going to have concave up. This means we have a relative min at x equals 0. Okay, then we check f double prime of negative 1. So negative 36 times negative 1 squared is negative 36. Negative 36 plus 12 is a negative 24. So that means that this is concave down, which will give us a relative max at x equals negative 1. And then finally, f double prime of 1 will also give us an output of negative 24. So that means this is concave down, which means we have a relative max at x equals 1. Now to get the actual points for the relative max and the relative min. Whenever you're getting the actual point, you plug those values where we have relative maxes and mins into the original function. All right, so let's go ahead and do that. So we said we have a min at x is 0, and we have relative maxes at -1 and 1. So plugging that into the original function to get our y coordinate, plugging 0 in, we get 0. Plugging -1 and 1 in is going to be the same because they're raised to even powers. So let's just do the negative. So that's -3 to the -1 times -1 to the 4th. 6 times -1 squared, which will give me -3 times +1 plus 6 times +1, or an output of 3. Okay, and finally our last example. G of x is a function such that g prime is of -3 is 0, g prime of -1 is 0, g prime of 0 is 0, g prime of 2 is 0. If g double prime of -3 is 4, g double prime of -1 is -2, g double prime of 0 is 0, and g double prime of 1 is 5, and g double prime of 2 is 3, find the x values of the relative max and relative min values when possible. All right, so something to notice here is with all of these first derivatives, the outputs are all 0. So what that means, if my first derivative at an x value is 0, that means that those are my critical numbers. So I have critical numbers at x equals -3, -1, 0, and 2. Okay, so we are trying to determine, without an actual function, if I have maxes or mins, when possible, at these x values. So since I have the outputs for each of these critical numbers for the second derivative, we are going to use the second derivative test. So with the second derivative test, we have g double prime at -3. So the output of the second derivative at -3 is 4, which is positive. So that's going to be concave up. The output of the second derivative at x equals -1 is a -2. So that would be negative or concave down. Now at 0, my second derivative is 0. So this is an example of this test being inconclusive. It's not possible for us to determine with the information given if we have a max or a min at 0. So this one's kind of just that we don't know and we don't have enough information to determine that. So that one is like not possible, no answer with the information given. And then g double prime of 1 is 5. That isn't really applicable here because 1 was not one of our critical numbers. And then g double prime of 2 is 3, which is positive. So that is concave up. So what that means is we have a relative min at -3 and at 2 at x equals -3 and 2. And then we have a relative max at x equals -1. So we're not able to actually find what that maximum output is or that minimum output is because we don't actually have the original function. So note, this was just asking us for the x values where these happen, not what they actually are. So again, test was inconclusive here. If you ever get an output of 0, it means you have to revert back to the first derivative test if possible. So the second derivative test is just kind of one that you use if the information only allows that, or if you're specifically requested to do so. All right, guys, that is it. We will talk about this tomorrow, and like I said, we're going to go over sketching the graph of the first derivative and second derivative from the original function, which kind of helps solidify this idea of concavity. Hope you have a good night.